So chapter 2 was called Basic Building Blocks, and it's where we were first introduced to the idea of elements and compounds and symbols in the periodic table. The first thing we did was we looked at elements versus compounds. We defined each of them. Elements are pure, unique substances that cannot be broken down into simpler substances. They are made up of only one type of atom. And really important in the definition is one type of atom. We're not saying elements are one singular atom because we can have diatomic elements like H2 or Br2, but it's only one single type or kind of atom. All the elements in existence are located on the periodic table. All right, we can find about 118 of them there. And I've listed some here as examples: gold, copper, zinc, sodium, helium, and hydrogen. Again, hydrogen we're writing as H2 because it's a diatomic element. Elements can be monatomic or diatomic. Monatomic meaning they exist as singular atoms as their base unit, where diatomic elements don't exist as singular atoms. They exist as two atoms bonded together in a molecule. So like H2, you're never going to find individual hydrogen atoms in nature, but they will always be together bonded in a hydrogen molecule. Compounds, on the other hand, we get if we start chemically bonding different atoms together. So compounds are a pure substance. It's a combination of two or more elements in a fixed ratio. And if we break that definition down, both elements and compounds are classified as pure substances because in an element, the smallest particle that we can get is the same particle. Meaning, in a sample of gold, the smallest, simplest piece of gold we can get are gold atoms, and all of those gold atoms are identical to each other. That's what a pure substance means. The smallest particle we can get for the substance are going to be identical. Zinc exists as only zinc atoms. They're all identical. But compounds are also considered pure substances because in water, the smallest particle of water is not a water atom, but a water molecule. And every single water molecule is going to be identical to every other water molecule. NaCl is a compound because each NaCl unit is identical to every other NaCl unit in the compound. So that's how they're both considered pure substances. It's important to understand that difference. So compounds are a combination of two or more elements in a fixed ratio, meaning that water as a compound is made up of two different elements, hydrogen and oxygen, and the way they are bonded is always going to be two hydrogens to one oxygen, so that ratio of 2 to 1. If it's not in that ratio, it's not H2O, it's not water. Sodium chloride bonds in a ratio of 1 sodium ion to 1 chloride ion. If it's not in that ratio, it's not sodium chloride. So the fixed ratio aspect of a compound is super important in understanding the definition of what a compound is. We looked at chemical formulas briefly, and we looked at subscripts and what they mean, what the chemical symbols are representing for the elements, and basically how a formula of a substance is written and how we can put those symbols and subscripts together to get different compounds. Basically, subscripts are showing us if we have more than one of an element. So in this compound, looks really confusing and complex, but what we're, just as an example, it's showing us that in this compound I have one, or in one unit of this compound, I have one platinum atom, I have two chlorine atoms, and I have two ammonia molecules, which is what this 2 is representing. And ammonia is NH3. So in each ammonia molecule, there's 1 nitrogen and 3 hydrogens. So when I have 2 ammonia molecules, I must have 2 nitrogens and 6 hydrogens. That's what that's saying there. So you should be familiar with that, being able to count up the number of atoms in a compound, like the examples we looked at here and the examples we looked at in the beginning of the year. We looked briefly at solids, liquids, and gases. We use those symbols next to a compound or an element to signify the phase that the substance is in. Remember that aqueous is an additional phase of matter. That means the substance is not solid, liquid, or gas, but it's however it exists at room temperature, just that it's dissolved in water. So Aqueous is a really specific phase of matter. We looked at particle diagrams for solids, liquids, and gases. Solids being very rigid, they have a fixed shape and volume, meaning the particles, if we were to draw them out, are going to be very close together. Liquid particles are a bit more random than solids, and gases are the most random. They're very far apart, moving in that constant random straight line motion that we talked about when we looked at gas laws. We used particle diagrams to also classify whether we have an element or a compound or a mixture of the two. And going back to our definition of elements and compounds, we can see how the definition is reflected in the particle diagram. These are made up of one type of atom. These are made up of two or more types of atoms bonded together. Right? Pure substance because I see the same type of particle. Pure substance because I see the same type of particle. But a mixture is not a pure substance. And we also went into detail about what the mixture is made of. So for example, this mixture is two different elements. This mixture is two different elements, one monatomic, one diatomic. This mixture is two different elements, both diatomic. And this mixture is a mixture of an element and a compound. So you should be familiar with that. We looked at those examples in the beginning of the year as well. We did a 2-day lab called the copper cycle. And in this lab, we started with solid copper powder. And we caused that copper powder to undergo several different changes. We added nitric acid, and then we added copper nitrate. We added sodium hydroxide. We added sulfuric acid, and added zinc. And we observed all the different changes along the way. And then when all was said and done, we ended back up with the solid copper powder again. So the copper cycle was really used to introduce a couple of important ideas. One was the law of conservation of matter, or the law of conservation of mass, which is the idea that if we measure the amount of copper that we started with, we should have ended with the same exact amount of copper, because matter cannot be created nor destroyed in a chemical process. Second was the idea that we tried to change the copper into something else, but in every step along the way, in that cycle, the copper was there in some way, shape, or form. So in this first step, there was brown gas that was formed. The copper didn't leave with the brown gas. The copper was here in the copper nitrate solution, right? So here was the copper, and here was the copper after that first step. Not an element anymore, but in a compound bound to nitrate. Then when we added sodium hydroxide, the copper was there this time in the form of copper hydroxide. And then when we heated it, it turned into copper oxide, different compound. Added the sulfuric acid, was now in copper sulfate. And then once we added the zinc, a reaction happened to get us the original elemental copper back. So we have this idea that the copper was there the entire time. So we couldn't just change the copper into something else, because copper is copper. And the only thing that it can do is bond with other things, unbond with other things. We can't just have elements that are magically popping into existence or just changing from one element into another in a chemical reaction, right? That's important. We then looked at an introduction to the periodic table. We observed the element boxes in the periodic table, which was composed of the element name, the element symbol, the atomic number, and the average atomic mass, which we get into in the next chapter. We looked at very basic periodic table vocabulary. So groups are the columns in the periodic table, and the rows are the periods. We looked at differences between metals, nonmetals, and metalloids. Metals compose most of the periodic table, right? They're on the left-hand side, nonmetals are on this side, and the metalloids are along this step that helps to nicely separate the metals from the nonmetals. We looked at properties of metals versus nonmetals. Metals are lustrous, meaning they're shiny, they're good conductors of heat and electricity, they have high melting points, they can bend, they're malleable, they're usually solid at room temperature, one exception being mercury, right? Nonmetals pretty much have the opposite properties. They're not lustrous, they're dull, they're not good conductors, they're non-ductile, they're brittle. And the nonmetals exist as solids and liquids and gases at room temperature. The metalloids, as we would predict, have properties somewhere in between. Some metalloids are more like a metal, some are more like a nonmetal, but they have properties that are shared amongst both metals and nonmetals. We looked at some trends in the periodic table. There are specific group names that we should be familiar with. Group 1 was the alkali metals. Group 2 were the alkaline earth metals. 3 through 12 were the transition metals. Group 17 were the halogens. And group 18 were the noble gases. We have the two blocks of elements down here. The first row are the lanthanides, and the second row are the actinides, right? They should belong right here in the table, but they're removed just really for ease of printing and keeping the table as compact as possible. In terms of phases of the elements, most of the elements are solid at room temperature. Remember, anything can change phase if we heat it up or cool it down, but at room temperature, most of the elements are solids. The open boxes here, all the white boxes, are representing the solids at room temperature. Elements that are liquids, mercury being the important metal exception, that's a liquid, and bromine is the only non-metal that's a liquid. Gallium is one we looked at whose melting point really hovers around room temperature. Mostly a solid, but it can melt around room temperature a little bit above, usually like body temperature. Holding it in your hand is enough to melt it. The gases here are in yellow. So if we know the gases, which are the noble gases, right? And then chlorine, fluorine, oxygen, nitrogen, hydrogen, and we know those two liquids, then everything else to us is a solid at room temperature. That's the easiest way to remember it. The last thing we looked at in this chapter were general trends in reactivity of the elements. I did some demos with magnesium and calcium and potassium and sodium. And the conclusions that we came up with were there were two areas of the table that were the most reactive. We have down here where francium is, right? The most reactive metal. And then up here where fluorine is, the most reactive nonmetal. The exception here are the noble gases, right? Group 18, they're called noble gases because they don't react, so we don't even talk about them in terms of reactivity. But we get these two opposite trends. So on the metal side of the table, they increase in reactivity down a group, but the nonmetals increase in reactivity up towards the top of the group. So we get this diagonal trend here where those upper right and lower left corners of the table are the most reactive elements, metals down to the lower left, nonmetals to the upper right, and in the middle we have some elements that are reactive. They react, but they're not as reactive as those 2 points in the table. One group that we highlighted specifically were the coinage metals. Sometimes they're called the inert metals, but the coinage metals are called such because they are used, or were at one point used, for making money or making coins, because they are so non-reactive compared to the other elements on the table. These trends were the last thing that we studied in this chapter, and this brings us to the end of our chapter 2 review.